In continuing with refraction, when light rays enter a new medium, they are going to change in speed because one medium is going to be more or less dense than the previous medium. When this happens, the light rays change direction. So here we can see what is often called an optical illusion because we perceive things by their light rays reflecting off of them. We see this straw because light rays are reflecting off of that straw and coming to our eyes. So if the straw is in the water, then the light rays reflecting off the straw coming back to us must travel from the water to the air to get to our eyes. So they're going to bend. And so we kind of see a bend in the straw as those light waves have changed speeds, causing it to bend. And here you can see as we see the straw here, it's just air between us and the straw. But here there is also water, so those light waves are bending. Once again, they are refracting as they come to our eyes, causing us to see this much bigger straw in a different position. So it's the refraction of light that is responsible for this optical illusion. Same thing, you can do this, you can try this at home. The light rays are bending because this medium of air and this medium of water are different densities, causing those light waves to travel at different speeds, coming back to our eyes, because once again we see things because we see those light rays reflected off of those substances. That is what we see. That is how light causes us to see things. So as you move the pencil around, you see that those light waves bend differently because of our viewpoint. We see things that are obviously not happening. Refraction causes those optical illusions. So any kind of bending of light from air to water is going to change mediums. Water to air changes mediums. Water to glass changes mediums, which is why, especially when there's water is in the glass and the pencil's in the middle, there's several changes in the speed of the light causing those multiple differences in what we see. So the index of refraction, obviously very important. It tells us how much light bends when it enters a new medium. So you can see this gentleman here is trying to go fishing here, trying to get some dinner. And you have the fish, which is right here, but he does not see the fish right there because of the bending of the light. He sees the fish here. So when he goes to try and get that fish, he's going to miss because of, that's right, physics. That's how we explain what's going on. So the index of refraction would be something he would want to know. What's the index of refraction between air and water? Well, I need to know that so that I'll know how to correct my aim when I try to fish. So the index of refraction tells us how much that light bends as it enters a new medium. There's another term called diffraction, a little different than refraction, but since the root here is the same, you can probably assume that we're talking about the bending of light waves, okay, and diffraction is the bending of light waves around a barrier. You see here, there's light waves going in or through these two holes cut out, and there's a bar in the middle, but since the light waves bend around that bar, you don't see the bar here because of diffraction. Those light waves have bent around the bar, so you don't see it in the light that is reaching the second wall because the light waves have bent around that barrier. Diffraction, refraction, reflection, those all happen for all kinds of waves, not just light waves, but here we're using examples of light waves because we're talking about electromagnetic radiation. We will talk about refraction, reflection, diffraction again when we talk about sound waves. So, what do all these things mean? What do they do in nature? Well, you have refraction and reflection, and then more refraction combining with droplets of water that you might have in the sky after a rainstorm to cause a rainbow. As the sunlight comes in, it is diffracted as it enters the droplet from the air to the water droplet, then it is reflected off of the water droplet, and then diffracted again as it comes out of the water droplet. And obviously this happens billions of times in the air because there's billions of water droplets there, causing us to see the many colors of the visible light spectrum because of that refraction of light. So, looking at these electromagnetic spectrum waves again, this is the same picture we've seen. Your low frequency radio waves, that have low power, are on the left side of the spectrum. The spectrum gets more powerful as we move to the right. When we get to gamma rays, they're very powerful, very dangerous for us. We don't want to mess with gamma radiation. Once again, this very small portion of the electromagnetic spectrum is the spectrum we can see, and we call this the visible light spectrum. Easily to remember, Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. Here is that spectrum again. You can see maybe a example of the size of the wavelengths here. Maybe a radio wave might have a wavelength the size of a soccer field or a house. And then as we move up, microwaves, they might be the size of a baseball. Continuing to move, infrared radiation, maybe the size of a cell is the wavelength. And then as we move on, obviously these very short wavelengths are very, very, very tiny. Here we get radio waves. We can emit them from radio towers. FM radios, right? Microwaves are emitted by microwave ovens, also by radar towers. Okay, people can emit infrared radiation because of our thermal energy, our body heat. Light bulbs can obviously do the same thing. Light bulbs emit the visible light radiation, ultraviolet, X-rays, and gamma rays coming from more dangerous things. Alright, so I'm going to look light and its uses. How do we use light? We obviously use light to see ourselves, right? Exactly. We see the reflection of light off of objects. That is what we see. So we can talk about what we might see from a plane mirror. That's called a flat mirror, right? It's going to show us a reverse image of ourselves because it's a reflected image, right? It's the exact opposite. And it comes from the direct reflection of light waves. That's how we use mirrors to see ourselves, through reflection. You might have a different kind of mirror. You might have a convex mirror. As you can see, a convex mirror is curved outward. It's much like the mirrors that you see in the hallways and stairwells at school, allowing us to see a large field of vision. A large field of vision lets us see a greater area of things, but everything's smaller, but we can still see a much greater area. You can see how light reflection happens on a convex mirror. It changes, right? It changes the direction of the light, which is what gives us the effect of the smaller images, but it lets us see a much greater field of view. A concave mirror, the opposite of a convex mirror, it curves inward like this, and that's something that's going to enlarge that image. It's going to make something bigger, so because it focuses the light. We might use this for a makeup mirror or a magnifying mirror, something that lets you see your face a little more larger. Once again, concave mirrors make things appear bigger than they actually are. Now we can talk about some lenses. You have convex lenses, which, as you can tell, it looks a lot like that convex mirror, only a lens allows light to go through it, all the way through it. So a convex lens is going to be thicker in the middle than at the edges. It's going to bring some light together, and it's going to make objects appear larger, like a magnifying glass. That would be a good use of a convex lens. Concave lenses are the opposite of that convex lens. Once again, just like convex and concave mirrors are opposites, convex lenses and concave lenses are opposites. So a concave lens is thicker at the ends than it is in the center, and it's going to make objects appear smaller than they really are. Makes objects appear smaller than they really are because of the way the light is bent. Because of that refraction of light, objects appear smaller in concave lenses. And that is all for electromagnetic radiation and how it affects us and how we use it. Specifically, the light waves, remembering that all electromagnetic radiation is transverse waves.